Welcome guys. In this video we are going to learn about fundamental sets. What is a fundamental set? So to understand what is a fundamental set, let us consider an nth order homogeneous linear differential equation. So consider an nth order homogeneous linear differential equation given to us by a raised to the power of, or a subscript n, sorry, and then yn, that's the nth derivative of y. Then we have plus an minus 1 yn minus 1 plus an minus 2 yn minus 2, then plus dots plus a2, and I'll have y dots, okay, and plus a1, we have y dots, and plus a naught y equal to 0. So consider an nth order homogeneous linear differential equation given to us by this expression. So this differential equation can yield n solutions. Okay, we have y1 of t, y2 of t, y n minus 2 of t, yn minus 1 of t, and yn of t. Okay, so these are n solutions that are possible from these homogeneous differential equations, okay, that are defined and continuous on some interval a b. Okay, so this a is less than b, and our independent variable must be chosen in between a and b. Okay, so something like this. So the differential equation above can yield n solutions, which is y1 of t, y2 of t, up to yn of t. Okay, n possible solutions, and we are now assuming that these differential solutions are actually defined and continuous on some particular interval a comma b, where a is less than b, and our independent variable for the purpose of this particular study should be chosen in between the interval a comma b. Okay, that is what this last statement means. Then the only criteria for us to judge that this set of solutions is a fundamental set. Okay, let me write it now. Then the solutions y1 of t, y2 of t, and so on up to yn of t form a fundamental set. Okay, if these solutions are linearly independent. I might not really dive so deep into the concept of linear independence in this video for now, maybe assuming that you might know it, but trust me if you don't know it. In the next video I'm explaining about linear dependence and linear independence in detail. But just know that for some particular solutions to form a fundamental set, that means they must be linearly independent. So each of these n different solutions that emanates from this second order differential equation, this nth order differential equation, sorry, I said second order, this nth order differential equation, homogeneous differential equation, all of the solutions, they should be linearly independent. So if they are linearly independent, then they form a fundamental set. Okay, so these solutions form a fundamental set if they are linearly independent. And the implication for linearly independence is that one of the quickest tests we use for linear dependence and linear independence is using the Wronskian. So that is the Wronskian of these solutions y1, y2 up to yn should not be equal to 0. Is that okay? So this is the criteria. Now there's something we need to just learn, just to introduce us to Wronskian linear dependence and linear independence. So this is how Wronskian is. The Wronskian of some solutions y1, okay, y2 up to yn is actually going to be a matrix. Okay, you're going to find the determinant of some n by n matrix, okay, formed by y1, y2, y3 up to yn. Then I'm now going to differentiate y1 prime, y2 prime, y3 prime, yn. So you differentiate y1 prime prime, y2 prime prime, y3 prime prime up to yn prime. So you're going to keep differentiating until you get to y1. So the n minus 1th derivative here will be y2, the n minus 1th derivative, y3, the n minus 1th derivative, and you keep going till you get to yn and the n minus 1th derivative of yn. So this is how to form your Wronskian matrix. You don't have to learn too much about it now because I'm explaining it in detail in the next video. And our Wronskian is defined in such a way that if the Wronskian is equal to 0, then we have the case of linear dependence. Okay, but if the Wronskian is not 0, we have linear independence. So to connect the dots on today's lessons, okay, to connect the dots on today's lessons, we have now said that a fundamental set satisfies the following properties. Okay, we have first of all that the solutions are linearly independent. And since the solutions are linearly independent, that means their Wronskian is not equal to 0. So using these two criteria, or using these two points, you can be able to tell if you have a fundamental set or not. So I'm going to solve with one example and wrap up today's video. So stay tuned for the example. So here we have this example. We want to solve y prime prime minus 5y prime plus 4y equal to 0. Then we are asked if the solutions of this equation form a fundamental set. So let's find out together. So solution. Now to solve it, start with your homogeneous second order differential equation. So the characteristic equation is, I'm going to use the variable capital D. We have d squared minus 5d plus 4 equal to 0. I hope you still remember how to form the characteristic equation. If you don't, watch my previous video there. They are explained fully there. So solving this characteristic equation, you have a plethora of methods to select from. I'm going to use factorization. It's more easier. I have d minus 1 and d minus 4 equal to 0. So solving, I have d is equal to 1 or d is equal to 4. So having obtained these roots from our characteristic equation 1 and 4, we can now have two solutions. Okay, so one possible solution is That's in our y1 case, we can have exponential x, that's exponential 1x. Then in another scenario, we can have exponential 4x for our solutions. Okay, so take note, your general solution is seen as a combination with arbitrary constants of your solutions gotten from the roots of the equation. So you use arbitrary constants and you do some principle of superposition, okay, to get your general solution. So this is how we normally express our general solution. That's c1 exponential x plus c2 exponential 4x. So I'm not going to express my solutions in terms of the general solution now, because I want to use the base form of these solutions to be able to determine whether the solutions are linearly dependent or linearly independent. Okay, so we want to check if the solutions actually form a fundamental set. So does y1 and y2 form a fundamental set? So to find out, we have to take the Wronskian of y1 and y2. So y1 and y2, okay, which are both functions of x. Okay, so how did I assume generally that they are functions of x? So you are giving y prime prime, right? Y prime and y. So whenever your differential equation is expressed like this, usually we like using y prime prime, and so on and so forth to denote that y is a function of x. Okay, but when you're giving it as y dot dot y dot and y, then you're actually denoting your y as a function of t. Is that okay? So the dots expressions are usually for time variables, then the primes we can use it for displacement. So that is what I have noticed, although it may be different for some persons, but I think we can work with this. So we are taking the Wronskian of y1 and y2, which are functions of x, and the Wronskian is the determinant of this particular 2 by 2 matrix. Why is it a 2 by 2 matrix? Because we have two solutions, okay, y1 and y2. If you have 3 solutions, to be a 3 by 3 matrix. The first row of this matrix is the base form of your solutions, okay, exponential x and exponential 4x. Then the second row is the derivative, okay, and if there is a third row for 3 solution cases, it will also be the second derivative. You keep differentiating like that and like that and like that. So I just have 2, so just one derivative now for the second row. Derivative of exponential x is exponential x. Derivative of exponential 4x is 4 exponential 4x. So I want to find this determinant, which is the determinant of exponential x, exponential 4x, and 4 exponential 4x. So to make things simpler for yourself, you can factor out. So in the first column, I consider exponential x is common, so I factored it out and it will be 1, 1. In the second column, exponential 4x is common, so factoring out, you have 1 and 4. So this is a simpler way of finding what your determinants. If you notice some things that are common, factor them out. So my Wronskian of y1 and y2, which are both functions of x, is going to be exponential 5x by the law of indices, and you now have 4 times 1 is 4 minus 1. This gives me 3 exponential 5x, and clearly the Wronskian is not equal to 0. So when the Wronskian is not equal to 0, recall that this is the special case of what? Linear independence. So since the Wronskian of y1 and y2, what are the both functions of x, is not equal to 0, okay, y1, y2 are linearly independent. Hence, they form a fundamental set. So another way this question would have come is, why is it that these solutions will form a fundamental set? And the reason why y1 and y2 forms a fundamental set is simply because they are linearly independent. Okay, so that's just basically the theory about fundamental set, linear dependence, linear independence. Now in the next video, I'm going to be throwing more lights about Wronskian, linear dependence, and linear independence. I'm going to be showing you ways that you can easily solve some of the problems associated with finding Wronskian and finding if some solutions are linear dependent or linearly independent. So I hope you learned a lot from this video. Please like, subscribe, share, hit the notification to stay updated, post comments, just anything that you want me to attend, any question at all, I could look into it for you. So once again, stay tuned and be happy that you now know what fundamental sets is. So take good care of yourself. I'll see you in another video. Bye.